I thought of giving you just an overview of what the concept of balance looks like in ancient, not just science, but also in the ancient thought. Literature, I'm going to start with Homer. I figured that since the Odyssey by Nolan, now he's so popular, everybody's watching it. So it might have been nice to start with Homer, since everybody's thinking already about Homer. So let's see what Homer has to say about balance, if anything. And then I'm going to talk about Plato and Aristotle because, of course, we have to include them. Okay, here. So this is actually the roadmap. So I'm going to start with Homer, as I mentioned, the poets, and then the philosophers are going to be Plato and Aristotle. I'm going to read some very puzzling passages. So I have more questions than answers about these passages, but I thought that they were cool and just you have, I think, when you read this text, to suspend your judgment a little bit, in the sense that some things that these ancient authors are telling us seem very weird. And so it's hard to really try to understand what they're saying and why they're saying it. But at the same time, what I think is worth doing is really to see how they were trying to address important questions that are still relevant today from different angles, having different perspectives than what we use now today. And then I'm going to talk about the scientists. So this is the more technical part. And I'm going to introduce this text, which is, the title is Mechanical Problems, is attributed to Aristotle, but is pseudo-Aristotle. So it comes from the school of Aristotle, but was not really written by Aristotle, where we have a very nice introduction on what mechanics is about, the discipline of mechanics is about, and the lever, the study of the lever, the functioning of the lever is the focus of this text. And then finally, Archimedes, who, of course, proved in a geometrical way the law of equilibrium. So throughout the presentation, I decided to include some Greek because, as I said, I am a classicist. So what I really enjoy doing is translating these ancient texts and really paying attention to the words used. And so I highlighted these words in the texts that we're going to read. So equal, inclining, balance, weight, force, pair of scales, and lever. So you're going to see these words in ancient Greek throughout the text I'm going to present to you. So let's start with Homer, the Iliad, not the Odyssey. So a few passages from the Iliad, 3 passages. So the first one is this. I'm going to read these passages with you because maybe, I guess maybe you're not familiar with some of them. And so, okay, so let's read it. But when the sun god Helios in his course had reached mid-heaven, the father, namely Zeus, the father of the gods, stretched out his golden pair of scales, Cruseia et Titaine Talantam, and in them set 2 destinies of death that brings long suffering, one for the Trojans, tamers of horses, one for the Greeks, dressed in bronze tunics. After grasping the middle of the scales, he pulled them up, and the destined day of the Greeks sank. Their fates were laid to rest on fertile earth. The fates of the Trojans arose towards the white sky. So in this passage, we are in book 8 of the Iliad. So it means chapter 8 of the Iliad. We have, of course, the fight between the Greeks and the Trojans. And in this moment, Zeus is weighting the destinies of the Trojans and the Greeks to see who is going to win the battle that day. And the idea is that the heavier is using a scale. The heavier destiny represents the destiny of the people who are going to lose the battle that day. Okay. Here we have some interesting words, which I highlighted. Pair of scales, talanta in ancient Greek. The idea of pulling up these pair of scales after grasping them in the middle, and then one side, the side with the destiny of the Greeks, sinks, is the one that sinks, while the other one arises. And the word here is interesting for sinking, is erepe, from the verb repein, which means to sink, but also to incline. And this word is going to be important to us later. Next passage, this comes from book 22. We have more or less the same image, but this time the destiny is the destiny of two specific heroes, namely Achilles and Hector. So the passage is very similar, as I mentioned, because the Homeric language is formulaic, namely Homer always uses the same lines. He repeats the same lines very often when he's describing the same type of scene. So here we have, when one day, namely Achilles and Hector, reached the springs for the fourth time, they were running around Troy. So here is the moment when Achilles is chasing Hector right before killing him. So they are running around Troy. After they did that, after they ran around the walls of Troy for 4 times, Zeus stretched out his golden pair of scales, and in them set 2 destinies of death that brings along suffering, one for Achilles, one for horse Lord Hector. And grasping the middle of the scales, he pulled them up, and the destined day of Hector sank. So Hector is going to die because his destiny, the weight of his destiny, is heavier. And went to Hades, and Apollo left him. So after this moment, really, Achilles kills Hector. So here, Zeus is just basically making the destiny of Hector something that cannot change anymore. After this moment, after this weighting of the destiny of these 2 heroes, is basically fated for Hector to die. There is nothing, he cannot come back. Okay, so as I mentioned, pay attention to this idea of retain, to sink or incline one way or the other. The last passage is this one from the Iliad. This is an interesting image because while in the previous 2 images, you just have a scale with 2 arms of the same length, and then you are just seeing which one of the 2 destinies is heavier. You're not really creating balance. You're just measuring which one is heavier. Here, you are actually creating balance because you want to weight you want to weight an amount of wool, as we're going to see. So here is the image. Everywhere, walls and battlements were wet with blood from both the Trojans and the Greeks. And yet the Trojans could not rout the Greeks. Still, they, so the Greeks, held steady as a careful woman, a worker skillful with her hands, holds steady a pair of scales and pulls up the wool and weight, keeping them heavenly balanced, Isazusa, so that she can earn a pitiful allowance for her children. So heavenly the battle stretched until Zeus gave the very highest glory to Hector, son of Priam. So the image that we get here is that the Trojans and the Greeks are fighting against each other, and the Greeks are really trying to do their best to face the Trojans. And we have this idea that the battle is more or less even in this moment. The Greeks are trying their best in order to keep pushing against the Trojans in order not to lose against them. And Homer introduces this simile where we have this woman, a worker skillful with her hands. And what she's doing is she's using a scale, and she's balancing a certain amount of wool against a weight, a standard weight, in order to measure what the amount of wool is. And so we have this idea of balancing here, which is expressed with this verb, isazusa. Here I would like you to pay attention to this isa. Isos in ancient Greek means equal, okay? Okay. So these are the images that we get from the Homeric poems and the words that we get in the Homeric poems. We'll see why these are interesting and important in 1 second. Okay, let's move to Plato and Aristotle, the philosophers. So to my knowledge, one of the very first occurrences. I think the first one, but whenever you say, is the first person who said something, is the first time a certain word appears, you always have to be very careful. But from my understanding and just my research, it looks like the very first time the word for balance appears in ancient Greek literature is this passage from Plato. This is the word, actually here. Yeah, isoropia. This is the word for balance. This is the word that Archimedes is going to use to talk about balance in a technical sense on the equilibrium of planes. So let's see how Plato uses this word. And then you're also going to see why the passages from Homer are actually important and interesting to introduce the concept of balance. Okay, so let's read the passage from the Phaedo. This is a dialogue about the concept of the soul. Plato talks about the immortality of the soul. And in one passage in the Phaedo, he talks about the cosmos. And he argues that he tries to explain, to prove why the Earth is at the center of the cosmos and doesn't move from there. So he wants to prove the stability of the Earth, why the Earth doesn't move from the center of the cosmos. Okay, so Socrates says, I've been persuaded, said Socrates, first, that if the Earth is round and is in the center of the heaven, he has no need of air in order not to fall, or of any other such necessitation, but that all that is needed to hold it, there is the heaven's likeness to itself all around, and the earth's own equal balance. For something equally balanced, placed at the center of some like thing, will not be able to incline more or less in any direction, but thanks to its condition of likeness will remain without inclination. So this is a very interesting and also puzzling passage. So scholars have many opinions about this passage and how to interpret it. The things I would like you to pay attention to are listed here in this slide. So Plato, as I mentioned here, is trying to prove the stability of the Earth. And his argument is made up of a series of points. He makes geometrical claims. He says the Earth is spherical. It is located at the center with respect to the heavens. So Plato thought that the cosmos is spherical and the Earth is also spherical at the center of the cosmos. And physical claims. He says whatever material lies between the Earth and the heavens is irrelevant. The reason why he's making this claim because he's arguing against some of his predecessors who were trying to say, the Earth is there and doesn't move because there is water below it. So the Earth is floating on water. Floating, I mean, it's stable on water. But when there are earthquakes, it's because the water is moving. Or there is air compressing it above and below. Or according to others, there is a vortex which maintains the Earth in its place at the center. So he's arguing against his predecessors here, really. But then he makes other two physical claims. He says the parts of the heavens cannot be distinguished. There is likeness in the heavens, and the Earth is equally balanced. Here, the word that he uses for balance, as I mentioned, is isoropia. If you remember from Homer, this is a combination of the ideas of isos, equality, and repein, to sink or to incline. So really the idea behind the word isoropia, balance, is equal tendency to incline in opposite directions. Okay. Now, however, it's not fully clear in what sense the Earth is equally balanced because of the likeness of the heavens and the likeness of the Earth. What is this likeness? What is this homoiotes? What does it mean? Is it about the material, the matter of the heavens and the matter of the Earth? Is about the density? Is about what? What is this likeness? This is a big question. There is another passage, however, where Plato repeats these two ideas. The idea that the Earth is equally balanced because of the likeness of the heavens and of the likeness, and because of the likeness of the Earth. This is a very puzzling passage to me, and also to scholars in general. So let's read it together, since it's puzzling and challenging, why not? So this is from the Timaeus, which is, I think, one of the most puzzling, not even a dialogue, by Plato. In the Timaeus, Plato describes how the cosmos came to be. There is this divine entity, the demiurge, who created the cosmos and structured it in a very mathematical way, using proportions and using music. Okay, anyway, in the Timaeus, at a certain point, again, the idea that the Earth is equally balanced doesn't move because of the likeness of the heaven and the likeness of the Earth itself appear. Okay, and this is where it appears. So let's read the passage. How could you think to use such terms, namely above, below, appropriately, if further there is something solid and evenly balanced at the center of the universe? He could not move to any of the extreme points, because these are all alike in all directions. But if you could travel around it in a circle, you would repeatedly take a position at your own antipodes, and call the very same part of it now the part above and then the part below. For the whole universe, as we have just said, is spherical, and to say that some region of it is above and another is below makes no sense. The origin of these terms and the subjects to which they really apply, which explain how we have become accustomed to using them in dividing the world as a whole in this way, we must resolve by adopting the following supposition. Just notice that here the word for heavenly balance is a little bit different. It's not the one with isos plus repen, is a different word, is isopales. But you still have the isos here. For the pales, I try my best to look for the etymology, and it just looks like this is just how the word appears. And so it's unclear what the etymology of this second part here, or the second part is. But isos, equality is still there. Okay, now let's go on. So I'm going to keep reading this passage. And this is where it gets very puzzling, because this is a thought experiment. What Plato is telling us is a thought experiment. Because he says, so his point is, he wants to say that to think about the concepts of below and above, heavy and light, as we're going to see, these concepts are relative. They are not absolute. Let's see what he says. Imagine a man stepping onto that region of the universe that is the particular province of fire. According to Plato, fire is high up in the heavens, where the greatest mass of fire is gathered together and toward which other fire moves. Imagine further that he has the power to remove some parts of the fire and place them on scales. Here the word for scales is plastigas, so a different word from the one we saw in Homer, talenta. When he raises the beam to gun and drags the fire into the alien air, applying force to it, clearly the lesser quantity of fire somehow gives way to his force more easily than the greater. For when two things are raised by one and the same exertion, the lesser quantity will invariably yield more readily, and the greater, which offers more resistance, less readily to the force applied. And so the large quantity will be described as heavy and moving downward, and the small one as light and moving upward. Now, this is the very thing we must detect ourselves doing in our own region, so on Earth. When we stand on the Earth and wait out one Earth-like thing against another, and sometimes some Earth itself, we drag these things by force, contrary to their natural tendency, into the alien air. While both of them tend to cling to what is akin to them, Nevertheless, the smaller one will yield sooner and more readily than the larger one to the force we apply that introduces it into the alien stuff. Now, this is what we call light, and the region into which we force it to go, we call above. Their opposites, we call heavy and below. Okay, so in what we get from these passages, I mean, there are many questions. There are many, as I said, puzzling things in these passages. But I think what is interesting to me are these ideas. So it looks like likeness, the concept of likeness, which explains why, according to Plato, the likeness of the heavens and the likeness of the earth explain why the earth is evenly balanced at the center of the cosmos. This concept has to do with to be alike in all directions. And the way Plato seems to explain this idea in the Timaeus is that it doesn't matter where one stands on earth, the heavens look and behave the same way. And this idea has to do also, or informs us, about what Plato thought about the concept of weight. So basically, with the thought experiment that Plato is offering us in the Timaeus, he's saying, look, the region of fire, where fire is naturally located, is in the heavens. Why? Because we can see that fire naturally tends to go upwards if we are here, if we're standing on Earth. So the thought experiment is, imagine that you can travel all the way to the extremity of the cosmos, where fire is located. Imagine that you can grab two different amounts of fire, and then you step out of the region of fire in the heavens, and you are facing towards the center of the cosmos, so towards Earth. And what you notice is that the bigger amount of fire is going to look heavier to you because the fire is trying to go backwards, it's trying to go back to the region of fire where it belongs to. So in that situation, the bigger amount of fire is heavier and is going, if you are facing the center of the cosmos, is going downwards, which is towards the extremity of the cosmos. So in that context, with you, human being, facing the center of the cosmos, with the fire in your hand, the fire is pushing down, is pushing downwards, and is heavier compared to the smaller amount of fire. And in that context, something heavier is going towards the extremity of the cosmos. In that context, okay? Then he says, okay, now go back to reality, to our world, everyday reality. Take two amounts of earth, one heavier or one bigger, the other smaller. And then you are going to see that the bigger one, if you are on Earth, is going to look like it's heavier, and it goes downwards towards the center of Earth. So if you are on Earth, what is heavier and goes downwards is moving towards the center of Earth instead of towards the extremities. Does this make sense what I'm saying, or at least a thought experiment? Namely, based on where you are located, either at the extremities of the cosmos or at the center of the cosmos, and based on what your direction is, the concept of above and below and the concepts of heavy and light change. Okay, this is puzzling to me. This is very wise Plato claiming this. And it looks like he's claiming it because he's saying, this is what I mean with likeness. This is what I mean when I say that everything is all alike in the cosmos, because even the concepts of above and below, light and heavy, they're just relative. It's based on where you are, what you are looking at, what materials you are handling. It's a weird thing, I think. Anyway, other important words here, plastic scales, different from what we saw in Homer. So there are different ways in ancient Greek. to talk about scales, a pair of scales. Dugon, yoke of a plow, beam of a balance. So this is going to become a technical word for the beam of a balance. Okay. Now, Aristotle, of course, he read this passage in the Timaeus. He got that, Plato was interested in trying to explain the stability of the earth. He explained it by using this idea of heavenly balance and this idea of likeness. And to explain this idea of likeness, he talked about this weird thought experiment. And Aristotle is like, this doesn't make sense, of course. And so this is what Aristotle says. Heavy and light, then, are a set of things unconditionally and in relation to something else. So there are two ways you can think of heavy and light, either in a relative sense or in an absolute sense. For of things having heaviness, we say that one is lighter, the other is heavier. For example, bronze is heavier than wood. So in a relative sense, you can say that if the two objects are made up of different materials, let's say same volume, different materials, you can say that one is heavier, the other is lighter. So this is heavy and light in a relative sense. About the ones said unconditionally, so about the concept of heavy and light in absolute sense, nothing has been said by our predecessors, though about those in relation to something else, they did speak. For they do not say what heavy is and what light is, but only what heavier or lighter is in things that have heaviness. This will be clearer if we state it as follows. For some things always and naturally move spatially away from the center, while others do so toward the center. Among these, the ones that spatially move away from the center move upward, I say, the ones toward the center downward. For it is absurd not to think that there is up and down in the heaven, as some people claim. These people are Plato. For there is no up and down, they say, if indeed the heaven is similar in every direction. Again, this is what Plato says. And from whatever point a given person traverses it, he will come to his own antipodes. For our part, we say that the extremity of the universe is up, both up as regards position and as being by nature primary. And since the heaven has an extremity and a center, it is clear that there will be an up and a down, as even ordinary people say, except not on adequate grounds. The cause of this inadequacy is that they think that the heaven is not similar in every direction, but that the hemisphere above us is the only one, since if they suppose in addition that it was like this all around, with the center similarly related to all of it, they will say that the extremity is up, the center is down. We say then that the unconditionally light is what spatially moves upward, that is toward the extremity, and the unconditionally heavy is what spatially moves downward, that is toward the center. By contrast, we say that one thing is light or lighter in relation to something else when of two bodies having heaviness and being equal in mass, is the translation, the other by nature spatially moves downward faster. So the main ideas in this passage by Aristotle seem to be these. The concepts of heavy, light, above and below are not relative the way Aristotle's predecessors, of course Plato, claim. Instead, in relative terms, if you have two objects that possess weight, one can be heavier and the other lighter. In absolute terms, each element for Aristotle has his own natural place towards which it naturally tends to move. So fire by nature moves upward and earth by nature moves downward. What naturally moves upward is light. What naturally moves downward is heavy. What goes towards the extremity of the cosmos is light. What goes towards the center of the cosmos, so the earth, is heavy. It's just as simple as that. You don't have to think of moving to the extremity of the cosmos and then facing the earth and then measuring two different amounts of fire and be like, okay, this is heavier and it's going downward toward the extremity of the cosmos. This doesn't make sense. Fire is light because it goes upwards towards the extremity, period. Aristotle also says that if two things have weight and occupy the same space, the heavier one moves downward faster. Of course, this is what he claims. Here, the concept of weight is baros, which is going to become another important word in Archimedes. And so Aristotle says, okay, all these things that Plato says about the stability of the earth, they do not make full sense to me. The earth is stable at the center of the cosmos simply because the natural place, the natural location of earth is the center of the cosmos. That's where earth moves towards to naturally. So the earth is there because that's the place where it's meant to be. Okay, now let's move to the more technical part. So here are the two authors or texts I chose. Before talking about Archimedes, I wanted to talk about this text because I think it's very interesting, just also as an introduction to the discipline of mechanics. So if you read Plato, you are not going to find anywhere Mechanica Techne. It doesn't talk about mechanics. Okay, it talks about other things that might remind us of mechanics, but not, it doesn't use the word Mechanica Techne. It's not there. Aristotle talks about Mechanica Techne in the posterior analytics, and there is very interesting the way he talks about it, because he lays out the sciences and he creates a hierarchy between sciences. And he says, Mechanica Techne, mechanics, depends upon stereometry, namely solid geometry. Okay, this is an interesting idea. The idea seems to be that in order to explain, to prove things in mechanics, you have to rely on geometry, on solid geometry more specifically. Okay. Aristotle really doesn't spell out much what he means by this. I mean, his focus is to talk about the sciences in general. So he's not focusing on the relationship between geometry and mechanics. But then we have this text, which comes from the school of Aristotle. So we say pseudo-Aristotle, because, yeah, it comes from the school of Aristotle, but was not written by Aristotle. The title is Mechanical Problems. Again, it's a puzzling text. But I think the main idea inside this text, which I'm going to mention in a moment, and especially the introduction is interesting. So this is the introduction, the very beginning of the mechanical problems. It says, our wonder is excited firstly by phenomena which occur in accordance with nature. Parafuses is nature, no? But of which we do not know the cause. And secondly, by those which are produced by art, via techne, from which technology, right? Like physics from fuses. Despite nature for the benefit of mankind. Nature often operates contrary to human interest, for she always follows the same course without deviation, whereas human interest is always changing. When, therefore, we have to do something contrary to nature, the difficulty of it causes us perplexity, and art has to be called to our aid. The kind of art which helps us in such perplexities we call mechanical skill, mekanen. Instances of these are those cases in which the less prevails over the greater, and where forces of small motive power move great weights. In fact, practically all those problems which we call mechanical problems. They are not quite identical, nor yet entirely unconnected with natural problems. They have something in common, both with mathematical and with natural speculations. For while mathematics demonstrates how phenomena come to pass, natural science demonstrates in what medium they occur. Among questions of a mechanical kind are included those which are connected with the lever. It seems strange that a great weight can be moved with but little force, and that when the addition of more weight is involved, For the very same weight, which one cannot move at all without a lever, one can move quite easily with it, in spite of the additional weight of the lever. The original cause of all such phenomena is the circle. Now, so the author of this text is saying many interesting things, and here are I think the important ideas, but there is so much more. So it tells us that the fundamental phenomenon that the art of mechanics, mechanical technique, deals with is how, by using a machine, and it focuses on the lever, one can move a large weight by applying a small force. This is something that causes wonder because it goes against nature. The idea of wonder is an idea that is always there in the ancient Greek mechanical treatises. There is the idea that you are making people say, wow, when you are doing things with these machines, because you're doing something that seems to go against what is our everyday life, what is natural. No, you are creating something that creates wonder in people. And it can also be beneficial to mankind. Now, he says, okay, the lever does something extraordinary, something that goes against nature, namely the lever as an object, as a tool, as an instrument, as a machine, is able to move a big weight by applying a small effort, a small force. And the author of this text is like, how is this possible? How can I understand the functioning of the lever from the point of view of how can this motion be produced? So the author of this text really pays attention to motion here, to the more kinematic aspect of the functioning of the lever. And he says, to understand how the lever moves and why I can use a lever to move a big weight with a small force, with a small effort, I should rely on the geometry of concentric circles. So I can reduce something mechanical to something geometrical. How? And here is the idea that the author has. If you think of concentric circles, and if you have the same radius, 2 points, one on the inner circle and one on the circle, the bigger circle, the same angular speed, the same angular, they're going, with the same angular velocity. What happens is that the point farther away from the center is transversing a bigger arc. So is moving faster compared to the point that is closer to the center. And so the author is saying, the author of the mechanical problems is saying, look, what happens with the lever is that the advantage that the longer arm has over the shorter arm has to do with the fact that the farther away you are from the center, from the fulcrum, your speed is greater. And this greater speed is what is giving you an advantage. Okay? And that's the way this author seems to understand the mechanical advantage of the lever. By noticing how you have points that move at different speeds because you are considering 2 arms of a lever, one is longer, the other is shorter, they are moving at the same time, but one is transversing a bigger arc of the circle. Okay, again, an interesting way to approach the question, the problem. Okay, now let's move finally to Archimedes on the equilibrium of planes. So I decided to give you the introduction where Archimedes lays out important postulates about the equilibrium of planes, and then we are going to read proposition 6 when he proves in a geometrical way the law of the lever. And so we are going to the law of equilibrium, balance, and we're going just to read the whole proposition. Okay, so first, pay attention to the title, on the equilibrium of planes or the centers of gravity of planes. This is the Greek. Epipedon isoropion e kentrabaron epipedon. Okay. So we have isoropion, you remember from already Homer, isos and repein, so equality and inclination. Then you have planes here, epipedon planes. So he's not talking about weights. He's talking about planes. But then you have an alternative title, the centers of gravity of planes. Here, centra, baron. Here you have weights. Okay, yeah, here is an interesting thing, which I am using Heath's translation, which is the standard translation, until Net publishes the translation. Anyway, so the author here chose gravity, but here the word is really weight, not gravity. Okay, is weight what we have there. So I decided to go with this translation because, as I mentioned, it's the standard. Heath is the guy who translated most of ancient Greek mathematics, so we have to pay respect to him, but yeah. The word there is weight. Okay, this concept of centers of gravity or centers of weight is very, very interesting. Archimedes never defines it, but we can guess what he has in mind, and we're going to see what he has in mind. So then, like every good ancient Greek mathematician, like Euclid, at the beginning of his treatise, he has a bunch of postulates, things that he doesn't have to prove, that are just true. It doesn't prove them. Okay? And these are the ones that you find at the beginning of on the equilibrium of planes. I postulate the following. Equal weights at equal distances are in equilibrium, and equal weights at unequal distances are not in equilibrium, but incline towards the weight which is at the greater distance. So this was number 1. 2. If, when weights at certain distances are in equilibrium, something be added to one of the weights, they are not in equilibrium, but inclined towards that weight to which the addition was made. 3. Similarly, if anything be taken away from one of the weights, they are not in equilibrium, but inclined towards the weight from which nothing was taken. 4. When equal and similar plane figures coincide if applied to one another, their centers of gravity similarly coincide. 5. In figures which are unequal but similar, the centers of gravity will be similarly situated. By points similarly situated in relation to similar figures, I mean points such that if straight lines be drawn from them to the equal angles, they make equal angles with the corresponding sides. 6. If magnitudes at certain distances be in equilibrium, other magnitudes equal to them will also be in equilibrium at the same distances. So a few ideas, I already mentioned some of them, that emerge from these postulates. Again, there is so much more one can say about these postulates, but some ideas are these. So Archimedes really seems to, just from the words that he uses, he seems to assimilate the concepts of baros, weight, and the concepts of megathos, magnitude. So it really looks like, yes, so of course the concept of baros belongs to physics. The concept of megathos is something that you find in ancient Greek geometry everywhere, a magnitude, which can either be a plane surface or a volume. So it really looks like Archimedes is saying, yeah, I mean, what we're talking about, what I'm going to talk about in this on equilibrium of planes has to do with the equilibrium of objects that have weights. But the way I'm thinking about these objects is in terms of geometrical magnitudes, is in terms of plane figures and solid figures. So the idea seems to be that, now, if you assume that the object is composed, these geometrical objects are composed of homogeneous matter, then you can reduce the weight of the object to either the area or the volume of that object, which is what basically Archimedes seems to do. Okay, so this is an interesting idea, again, no? From baros, from weight to megathos, magnitude. Then I already mentioned this, so isoropia, isos and retain, incline, so the word balance, which here is used in a technical sense. So in Plato, we have this idea of the Earth is evenly balanced, but it's unclear exactly. I mean, we don't have two weights balance. It's just the Earth. So what it really means, I mean, it's not, here we really have the technical meaning of the word balance explained in a technical sense. So it's balance between two weights or magnitudes. Then there is a big question of what the center of gravity or the center of weight is and what its role is. So to understand a little bit more these ideas, let's read proposition 6 in the on equilibrium of planes. So at least this is the number that we find in the edition, but then actually the number is different. Anyway, proposition 6 says, two commensurable magnitudes, so not weights, magnitudes, balance at distances reciprocally proportional to the magnitudes. Okay. Commensurable means that they have a common measure, okay? Two magnitudes that have a common measure. Okay, suppose the magnitudes A, B to be commensurable, and the points A, B to be their center of gravity. I'm going to mention what the center of gravity is in 1 second. Let DE be a straight line so divided at C that A is to B like DC is to C. We have then to prove that if A be placed at E and B at D, C is the center of gravity of the two taken together. So they are balancing. So this is my magnitude A, this is my other magnitude B. I imagine this line, which is basically my balance. This is the fulcrum. And I'm saying that A has to be, A is to B, like DC is to C. Okay. Let's move on. Since A and B are commensurable, so are DC, D. Okay. Let N be a common measure of DC, C. N is there. This is a common measure. Make DH, dk equal to C. So now we are modifying this image or are adding points and stretching it. So we create DH and dk equal to C. And EL produced on C equal to CD. Then EH is equal to CD. EH is equal to CD. Since DH is equal to C. Since DH is equal to C. Therefore, LH is bisected at E. So this whole thing, LH, is bisected here. As HK is bisected at D. So HK is bisected at D. Okay. Thus, LH, HK must each contain N, an even number of times. Take a magnitude O, so another magnitude O, such that O is contained as many times in A as N is contained in LH. Whence A is to O, like LH is to N. But B is to A as CE is to DC. And B is to A as HK is to LH. Hence, ex equali, B is to O as HK is to N. Or O is containing B as many times as N is containing HK. Thus, O is a common measure of A and B. So first, he tried to find a common measure in our balance, and then he tried to find a common measure in our magnitudes or weights. Okay, then he says, divide LH, HK into parts, each equal to N, and A and B into parts, each equal to O. The parts of A will therefore be equal in number to those of LH, and the parts of B equal in number to those of HK. So these parts, I divided A, and then B, I divided it into these equal parts. And there is a correspondence between the parts from LH to the parts, they correspond to the parts of A, and the parts of HK, they correspond to the part of B. Okay. Now it says, place one of the parts of A at the middle point of each of the parts N of LH, and one of the parts of B at the middle point of each of the parts of N of HK. So what is happening is basically distributing the weight of our first magnitude throughout this whole line, and he's distributing the weight of our second object throughout this other portion of the line. So, and here is what he says. Divide LK, HK into parts, each equal to N, and A, B into parts, each equal to O. The parts of A will therefore be equal in number to those of LH, and the parts of B equal in number to those of HK. Place one of the parts of A at the middle point of each of the parts N of LH, and one of the parts of B at the middle point of each of the parts of N, of HK. So, yeah, as I said, we are distributing the first weight here and the second weight here. Then he says, then the center of gravity of the parts of A placed at equal distances on LH will be at E. So this is the center of this distance. So the center of gravity of this whole weight, which is distributed along this distance, is going to be E, which is the center of my line below. And the same is true in the case of HK. So the center of gravity of the parts of B placed at equal distances along HK will be at D here, the middle point of HK. Thus, we may suppose A itself apply at E. So what we can do, or what we can derive from this thing that we just did, is that if this is the center of gravity of this whole weight, because I have distributed it along the entire line, and this is the center of it, then I can imagine the entire A, the entire weight of A has compressed in point A. And the same is true in this case. Since this weight I have distributed here, the center of this distribution is B. So I can imagine this weight to be compressed here in point B. So these 2 points, D and E, have to be the 2 points where if I locate the 2 weights there, then they're going to balance out. Actually, I didn't read the whole thing, but this is what is basically happening. Actually, let's read the whole thing. Thus, we may suppose A itself apply at E and B itself apply at D. But the system formed by the parts O of A and B together is a system of equal magnitudes, even in number and place at equal distances along LK. And since LE is equal to CD and C is equal to DC and LC is equal to CK, so that C is the middle point of LK. Therefore, C is the center of gravity of the system arranged along LK. Therefore, A acting at E and B acting at D balance about point C. So, this was the proof of the law of equilibrium in Archimedes. A few considerations. So, what Archimedes cares about is statics, how to explain how equilibrium works with 2 weights placed there, how they can stay there, how there is stability. So compared to the author of the mechanical problems, he's not focusing on the motion, he's focusing on statics. Second thing, the concept of center of gravity. So it looks like, for Archimedes, the concept of center of gravity can mean basically two things. Is, if you have a magnitude, is a point in a magnitude, in a surface or in a volume. Okay, so in a surface, in an area, or in a solid. Okay. From the point of view of physics, this center of gravity for Archimedes is basically the place where you can imagine that the entire weight of the object is compressed. So then you can think of a certain object, a certain magnitude, as being represented by that specific point, which is the center of gravity of that point. And this is just a reference to what he's doing in the method. So in the planes, on the equilibrium of planes, he proves the law of equilibrium. He talks about the concept of center of gravity or center of weight, the way I describe it. And then he tries to identify the center of weight of different geometrical figures. So for example, in the case of a triangle, the center of weight is going to be the intersection of the medians of the triangle. That is going to be the center of gravity or center of weight. Okay. Then in this other text, which is the method of mechanical theorems, which is a very weird, again, a very puzzling text. What Archimedes does is, I can use this law of equilibrium that I prove on the equilibrium of planes to try to figure out the relationship between the areas or the volumes of two geometrical objects, one of which I know what the area or the volume is, the other one I don't. But one of them is inscribed or circumscribed in the other. How? By balancing these two objects. Because if I balance these two objects, then I know what the distance between the two objects is. And since this is proportional to the areas or the volumes of the two objects, then I'm also able to figure out what the relationship between the two areas or the two volumes of the two objects is. So one of the very famous propositions is the one with a parabolic segment and a triangle inscribed inside it. The triangle is fine. I know how to determine the area. I know how to determine the center of weight. It's just the intersection of the medians. But then the parabolic segment is a more complex entity. And Archimedes wants to identify what the relationship between these two geometrical figures is. The relationship is the parabolic segment, the ratio of the parabolic segment, the area of the parabolic segment to the triangle is 4:3. Okay, so the parabolic segment is 4 times, it's 4 times, while the triangle is 3 times. And he figures out this relationship by balancing the two objects on a balance, really. That's the way he talks about an imaginary abstract balance. And so he locates them in such a way that the triangle, which is, let's say, the value is 3, is located here. Then you have the beam, which is 4. Then you have the arm of the beam, which is 4. And then you have the fulcrum. And then you have 3, the other side of the beam, the other side of the arm. And then you have your parabolic segment, which is 4. So it's balancing out these two areas. And by balancing them out, he's able to figure out what the relationship between these two areas is, using this mechanical theorem, as he describes it, because it has to do with mechanics and ballast, but he applies it to geometry to come up with a geometric solution, relationship between, to figure out a relationship between two geometric objects. So that's the way Archimedes proves the law of equilibrium using geometry, but also the way he uses this law of equilibrium, which he describes as something that has to do with mechanics, because of course it's something that has to do with objects that in theory have weight. But then he uses it, he borrows it, and he applies it to geometry to come up with something, with a solution to a geometric problem, namely the relationship between two areas of two different figures, one inscribed inside the other. This is a very complex, and also the start of this text is interesting, the method. Anyway, this was what I wanted to describe today. These are the translations I use and the bibliography I rely on. So thank you so much for your attention. It was super long, I'm sorry. Yeah. Okay.
Thank you.
Yes.
About this debate about from between Aristotle and Plato about absoluteness of up and down.
Yeah.
I've always been told that like each element has its own natural place, so it goes water. I'm sorry, earth, water, air, fire, and and then the heavens, right? And it sounded to me like you were saying that actually for Aristotle, fire just tends towards the extremity, so it always goes up. Whereas Plato seemed to be saying that no, it has this natural place just above the air, and if you move it either direction, it's going to try and go back. Is that just a different idea of where the natural place of fire is, according to Aristotle and Plato?
That's a fantastic question. They actually agree on what the natural places of different elements are.
Okay.
And indeed, that's what is very puzzling. Why Plato has to say you are at the extremity of the cosmos, where there is fire,
right.
Okay? Because the heavenly bodies are made of fire, the stars, fire is there. You are there, somehow, you travel all the way there. Okay. Then you stand and you face the center of the cosmos. So you are facing Earth, and you are moving these, you are taking these two pieces of fire with you, and you move to the region where there is air.
Right.
And then you are like, okay, fire is pulling down,
right.
Especially the bigger amount is really trying to go back. And this is a motion downward.
Right.
Why does it have, it's the same idea. It's going the same direction for both Plato and Aristotle. But why does Plato have to come up with this explanation where he says it's going downward? Just because I am in this direction myself, I'm facing the center of the cosmos. It's puzzling because Plato and Aristotle, they both agree that fire is up there and fire goes towards that direction.
But are they saying that, like, is the natural place of fire at the extremity? Or I always thought it was like between air and the quintessence, the stuff of the heavens. I thought there was.
Yes, Aristotle thinks that there is the ether. For Plato, is fire at the.
Oh, for Plato, fire is at the extremity.
Yeah.
And for Aristotle, fire's natural place is intermediary between the air and the.
Yeah, there is ether. Yeah.
And the ether. But I thought you were saying that for Aristotle, fire is just light and tends towards the extremities. Like, absolutely, it's always going up. But if its actual place is somewhere beneath the extremities, it would seem like if you pull fire up, it'll tend to go down. Down. Like if you pull it away from its natural place in either direction, it'll tend to go back to the natural place. Isn't that right?
So you mean like if you are in what? For Aristotle, it's just saying we are here on Earth, and I can see what fire is doing is always going up.
Relative to us, right? But
yes,
but if you were above the natural place of fire.
Yeah, if you are in the ether area, then you see fire going down towards. Okay. Yes, I guess Yeah, that is a good point. Yes, if you think of ether as the last section. Yes.
Okay, good.
It's true.
Okay.
It's true. It's a good point. It's a good point.
Wait. Okay. Thank you. This was fantastic. I love the proof of the equilibrium.
Did it make sense? Because at a certain point, I think I don't know if you noticed, but I was like, I stopped reading precisely because I thought that somebody said this doesn't make sense, and I was like, oh my gosh, I got something wrong, and so I got nervous. But it does. I mean,
well, it must have been someone smarter than me. But yeah. So I have one question. So what's fascinating about the so if you read like the like 19th century, 20th century historians of mechanics, right? And they talk about equilibrium and the ancients. They basically will say something, oh, you know, they can only think about it in terms of the balance, like they have these very limited concepts. And the interesting thing here, like of having the contrast with the philosophers and the scientists, or Archimedes in this case, is of course that the philosopher's notion of equilibrium is, just as your discussion with Wayne just showed, is like embedded in this much broader theory where you can have higher order explanation of why you get certain balances in certain places.
Yes.
Right? So you can reason in a much more general way about balances using this higher order theory. And my question is whether in Archimedes, of course, he is interested primarily in these statical problems, but whether him or others at the time who are doing statics also, if if they're asked, even though they're not applying it to the problems, would have a story to tell as to why weight is the way that it is, or why balances are the way that they are in the places that they are, or whether they're literally just shutting up about the higher order theory and just talking about the devices. Does that make sense?
Yeah, I think so. When it comes to Archimedes, he might have written a treatise on balance, which is lost. We only have on balance probably the object, the instrument. We only have the geometrical proofs and explanations. And from there, what we get is, on the equilibrium of planes, on floating bodies, where also the concept of equilibrium is being used, but this time applied to floating bodies. And then this very weird thing that is happening in the method, where he's using the concept of balance but applied to geometry. So that's what we have from Archimedes. Then in the mechanical tradition, they really care about the lever because they really care about the application. And they talk about the 5 fundamental machines. One is the lever, and which is the coolest one for them. But all of them work with the same principle of moving a big weight by using a small force, a small effort. And they were really trying to understand how these work.
In terms of the ratios of the sides and the magnitudes in the machines, right? They wouldn't have a story like Aristotle and Plato about why ultimately those particular ratios are caused or explained by the the natural places or something like that.
Yes. So I think in the pre-Socratic tradition, probably you read we have some pre-Socratics who talk about the fact that there is the principle of sufficient reason. There is no reason for the earth to move farther away where it is. Yeah, so we have fragments from, I think he's Anaximander, but not just Anaximander, also Thales, Anaximenes. They all try to understand why the earth doesn't move. So there is this super cool fragment by Thales where he says, the earth, since for Thales the principle, the most important element is water. He thinks that the earth is floating on water. And he says, it's normally stable, but when there are earthquakes, it's because the water below is moving. So, or you have Empedocles with the vortex idea. So they are thinking in terms of cosmos, in terms of, balance and equilibrium, more in terms of the cosmos. And Plato is picking up from them. Indeed, he's criticizing his predecessor. He says, I don't need water or air or a vortex to explain the stability. It's just that the earth is heavenly balanced. Why? Because of this likeness. And then the big question is, what do you mean with this likeness? And that's what you get in the Timaeus. Likeness, because it doesn't matter what direction you look at, is all alike. Because up and down, evident, that's clear.
Yeah, thank you. I'll quiz you more.
Yeah.
All right, so thanks a lot for the talk. Was very, very interesting. So I have a couple questions that probably are related to the discussion before. So one would be, speaking of like treatises in 19th century on mechanics, like when Ernst Mach discusses the example of the demonstration of the law of the lever by Archimedes, he talks about it in terms of using the term symmetry. And it seems from I mean, symmetry is also very much present in the Timaeus, of course, but it seems that there is no direct connection, right, between the way the lever is treated by these authors and this other concept of symmetry as like order or harmony and so on. Is there already, like in the Greeks, a connection between balance and symmetry, or are completely separate and it's
a great question. The fragment from Plato, from the Phaedo, there is an article, and it's in the bibliography, where the author, I don't remember the name, but they are arguing against interpreting that passage in Plato as an example of the concept of symmetry, the way it's understood in modern physics. And so they argue against that. What I can say, just based on, I don't have all the background when it comes to understanding the concept of symmetry the way you guys understand it. What I can say is that for sure, they care a lot about ratios, proportions. When in the Timaeus you have the demiurge creating the work, you have this super famous passage, which says the most beautiful bonds of all is analogia. Analogia is proportion, because it means anaton, auton, logon. It means according to the same ratio. And then it says the elements are four, and I am using all four of them because the cosmos is a solid reality. And so we are talking about a proportion with four numbers, not just three, because that would be a plane reality. And what he says, and I'm using the four elements, and I am creating a proportion between them, not just when it comes to the physical aspect of the cosmos, but also the so-called soul of the cosmos. You have proportion and musical ratios in there as well. So yeah, but I think what you're asking me about symmetry in this more modern, from the approach of modern physics, that article addresses better your question. So yeah.
I'm gonna insert myself. Sorry.
Yes. Oh, sorry.
In this,
yeah.
Just briefly, because I saw just now that you said, I think the mechanical problems that they attributed cause of all these mechanical problems to the circle.
Yes,
and
to the circle.
The circle of the spherical symmetry is a very important part of modern physics. I was wondering whether the reasoning Archimedes end up using with the balance has much to do with, I guess it's a lot to do with the circle, right? But like, how do you think it is related? Like the mathematical explanation of the balance in terms of circles versus like a physical thing of just balancing?
Yes, that's a great question. For the ancient Greeks always say that the spherical and the sphere are the most beautiful shapes, because there is no beginning, there is no end, doesn't matter where you are, it's the same distance. So, and the study of the cosmos is all about spherics, is all about study of the sphere. Yes, for sure, Archimedes has the sphere and the circle in mind as well, just because it's just something that is it appears so frequently, this idea, this concept of the circle and the sphere as the most beautiful, the most perfect object, and it's definitely there. So I think, yeah, it makes sense to me.
Oh, sorry, we're out of time, but please carry on for patience after the
Thank you so much for your time and your patience.